In this video, let us derive Lagrange's equation of motion from D'Alembert's principle. To derive Lagrange's equation of motion, let us consider a system consisting of n number of particles. The position vectors of this n number of particles can be described or expressed as the function of generalized coordinates qj's and the time t. For this system comprising of n particle, we can write the coordinate transformation equation as Ri, that is the position vector of n particles, as Ri equal to Ri is the function of q1, q2, q3 to qn, comma, time t. So this is the transformation equation for the n number of particles, and let us take this as equation number 1. Before moving into the next step, let us know a mathematical formula which is called as a chain rule or function of a function rule. So this rule helps us to get the total time derivative of a function which depends on more than one variable. Here we have a function f. This function f depends upon more than one variable. Here the function f depends upon both x and y. It involves two variables. To get the total time derivative of this function, that is df by dt, the formula goes like this: df by dx into dx by dt plus df by dy into dy by dt. This formula can be extended to any number of variables. For example, if the function involves three variables x, y and z, df by dt will be equal to df by dx into dx by dt plus df by dy plus into dy by dt plus df by dz into dz by dt. So this is the function of function rule or chain rule, which will help us to get the total time derivative of a function involving many variables. So we know equation 1 is Ri equal to Ri, it is the function of many variables q1, q2, q3 to qn, comma t. Next, let us differentiate this equation 1 with respect to time, or it is like finding the total time derivative of equation 1. Here we are making use of the chain rule. Using chain rule, dri by dt will be equal to dou ri by dou q1 into dq1 by dt plus dou ri by dou q2 into dq2 by dt plus dou ri by dou qn into dqn by dt plus dou ri by dou t into dt by dt. So this is expanded using function of the function rule. In the last term, dt and dt will get cancelled. In classical mechanics, a one-time differential is written as a dot product, and we know Ri is the position vector. So differential of this position vector with respect to time will give us velocity, that is Vi dou Ri by dou q1. dq1 by dt is written as q1 dot, that is one time differential of time. So q1 dot plus dou Ri by dou q2 into q2 dot plus dou Ri by dou qn into qn dot plus dou Ri by dou t. So using summation, we can write this velocity Vi is equal to summed over dou Ri by dou qj dot plus dou Ri by dou t. So here the summation j will run from j equal to 1 to n. So let us take this as equation number 2. And here the qj's are nothing but they are qj dots are nothing but they are the generalized velocities. Okay, then let us write an equation for virtual displacement. Already we have equation 2, that is dri by dt is equal to summed over j dou ri by dou qj into dqj by dt plus dou ri by dou t into dt by dt. Here, using the equation 2, we can write this virtual displacement, the small change in the position vector delta ri is equal to summed over j dou ri by dou qj into delta qj plus dou ri by dou t into delta t. But we know virtual displacements do not take much time, or they do not involve time, so we can write delta t equal to 0. So we get delta ri is equal to summed over dou ri by dou qj into delta qj. Since delta t is equal to 0, the last term will become 0. So this equation is named as equation 3. Now let us take any one of the particle in the system. For example, ith particle, which has mass mi, and this particle is acted upon by an external force Fi. So for when a particle is acted upon by an external force Fi, to keep the system in equilibrium, we can make use of the D'Alembert's principle. According to D'Alembert's principle, we have already seen in the previous video, summed over I Fi minus Pi dot into delta Ri equal to 0. This is the mathematical statement of D'Alembert's principle. Let us name it as equation 4. We have already the expression for delta Ri, that is the virtual displacement, in equation 3. Substituting equation 3 in 4, we get summation Fi minus Pi dot dou Ri by dou Qj into delta Qj equal to 0. Next, let us bring this dou Ri by dou Qj into delta Qj inside. We will get summed over Fi dou Ri by dou Qj into delta Qj minus Pi dot dou Ri by dou Qj into delta Qj equal to 0. Let us take this as equation number 5. Now, we have to evaluate the first term of the equation 5 and the second term of the equation 5 separately and put it together to get to get into the Lagrange's equation of motion. So first let us deal with the first part of the equation 5. The first part is Fi dou Ri by dou Qj into delta Qj. So in place of this Fi dou Ri by dou Qj, we are introducing a new notation, capital Qj into delta Qj. This is equation number 6. This Fi dou Ri by dou Qj equal to capital Qj is nothing but it is one of the component of generalized force. By observing this capital Qj, we conclude that capital Qj's, though they are the component of generalized force, they do not have the dimensions of the force. In the same way, this delta Qj's, though they look like a length or a distance, they do not have the dimensions of length, but their product capital Qj into delta Qj have the dimensions of work. So we have explained what is this equation, the first part of equation 5. Okay, we also know the momentum Pi is given by mass into velocity, that is mi into vi. In classical mechanics, this vi, the velocity is written as ri dot. So Pi dot will be equal to mi ri double dots. In this Pi dot, it is Pi dot. The third equation is Pi dot equal to mi ri double dot. So I have missed a dot here. See, the first equation is Pi equal to mi vi, mass into velocity. The second equation, vi is written as ri dot. Then it is Pi dot is equal to mi. We are differentiating the momentum again so that the ri dot is differentiated again. So it is mi ri double dot. Okay, now let us evaluate the second part of equation 5. The second part is Pi dot dou Ri by dou Qj into delta Qj. In place of Pi dot, let us write mi Ri double dot dou Ri by dou Qj into delta Qj. So here mi is the mass we know. We wanted to know what is this Ri double dot dou Ri by dou Qj into delta Qj. So we are interested in this. To evaluate this, what we do is we are doing d by dt of Ri dot dou Ri by dou Qj. Randomly we are taking this because we want Ri double dot dou Ri by dou Qj. To get the value of this, we are taking d by dt of Ri dot dou Ri by dou Qj. So inside the bracket Ri dot is u, dou Ri by dou Qj is v. We know d of uv is equal to udv plus vdu. We are making use of that formula. First we have to do u dv. So u is Ri dot, dv is d by dt of dou Ri by dou Qj plus v du. V is dou Ri by dou Qj. Du is d by dt of Ri dot. So in the next step, what I am doing is Ri dot, Ri dot into d by dt dou Ri by dou Qj plus, see, d by dt of Ri dot is double time differential, so it is Ri double dot. For my convenience, I am writing Ri double dot first, followed by dou Ri by dou Qj. So I am bringing this Ri double dot dou Ri by dou Qj to the left hand side, and on the right hand side we have d by dt of Ri dot dou Ri by dou Qj minus Ri dot d by dt of dou Ri by dou Qj. This is taken as equation number 8. Now let us substitute this value of Ri double dot dou Ri by dou Qj in equation 7. Substituting it, we get summed over pi dot dou Ri by dou Qj into delta Qj equal to summation mi into d by dt of Ri dot dou Ri by dou Qj minus Ri dot d by dt of dou Ri by dou Qj, everything into delta Qj. We know this Ri dot is equal to mi. That is one time differential of Ri dot is Ri dot is vi, that is the velocity. So we get d by dt of mi vi dou Ri by dou Qj minus, that we are bringing this mass inside first. First we are bringing the mass. So by that we get summation d by dt of mi vi dou Ri by dou Qj minus mi vi d by dt of dou Ri by dou Qj, entire thing multiplied by delta Qj. So we know equation number 2. Equation number 2 is vi is equal to summation dou Ri by dou Qj into delta Qj dot, Qj dot plus dou Ri by dou t. Now let us differentiate this equation number 2 with respect to Qj dot. So if I differentiate equation 2 with respect to Qj dot, I will get dou vi by dou Qj dot. So in the second term, do not have Qj dot, so the differentiating that will give you 0. And here when you differentiate dou Ri by dou Qj dot, differentiating the first term, we get dou Ri by dou Qj, the constant will come. The Qj dot is there. When you differentiate that, Qj dot by Qj dot will give you 1. So you will get dou vi by dou Qj dot equal to dou Ri by dou Qj. And also in that previous equation number 9, you would have got d by dt of dou Ri by dou Qj. And here this d by dt and dou by dou Qj can be interchanged. That is, differentials can be interchanged. So dou by dou Qj into dri by dt. We know dri by dt is Ri dot, and Ri dot is nothing but it is vi. So dou vi by dou Qj, this is taken as equation number 11. The substituting this equation number 10, 11 in equation 9, we get summation pi dot into dou Ri by dou Qj into delta Qj equal to summation d by dt mi vi. So dou vi by dou Qj, in place of this dou Ri by dou Qj, we get dou vi by dou Qj dot minus mi vi. In place of d by dt of dou Ri by dou Qj, we substitute dou vi by dou Qj, the entire thing multiplied by delta Qj. Now here you see, if I do dou by dou Qj dot of half mi vi square, we know this half mi vi square is nothing but it is the kinetic energy. If I differentiate this kinetic energy with respect to Qj dot, I will get 1 by 2 mi vi. When I differentiate vi square, I will get 2 that I have written in front, 2 vi into dou vi by dou Qj dot. This 2 and 2 and will get cancelled. We will get mi vi dou vi by dou Qj dot. So see here in this equation we have mi vi dou vi by dou Qj dot. In place of that we can write dou by dou qj dot of half mi vi square. So now substituting this half mi vi square in equation 12, we get d by dt of dou by dou qj dot of half mi vi square minus dou by dou qj of half mi vi square, everything into delta qj. So in place of this half mi vi square, we can write T, that is the total kinetic energy of the system. We get summation pi dot dou ri by dou qj into delta qj equal to summation d by dt dou t by dou qj dot minus dou t by dou qj, entire thing multiplied by delta qj. So we in equation 6 we have explained what is the first part of equation 5, and in equation 13 we have evaluated the second part. So substituting the values of equation 6 and 13 in equation 5. Equation 5 is fi dou ri by dou qj into delta qj minus pi dot dou ri by dou qj into delta qj. Substituting everything, we get the capital qj into delta qj minus d by dt of dou t by dou qj dot minus dou t by dou qj into delta qj is equal to 0. So in this we have delta qj as a common, so we can take it outside. Inside the bracket, we will have capital Qj minus d by dt dou t by dou qj dot minus dou t by dou qj. So the everything multiplied by delta qj equal to 0. But we have seen that these qj's are independent. q1, q2, q3 are independent of each other. So they will not vanish. That means delta qj will not be equal to 0. So to make the previous equation valid, we make this the terms inside the bracketed terms to be 0. So qj minus d by dt of dou t by dou qj dot minus dou t by dou qj is equal to 0. Now let us take this capital qj to the right hand side. We get d by dt of dou t by dou qj dot minus dou t by dou qj equal to capital Qj. This equation represents the general form of Lagrange's equation of motion. So from this general form of Lagrange's equation, we can derive the Lagrange's equation motion for a conservative system and a non-conservative system.